be with you guys for the physio part of the course. This I'm definitely biased, but I do think this is the most interesting of the topics. Hopefully, you guys do too, since you guys all want to go to doctor school. Let's see. Um, in the chat real quick. Alrighty. So I do things. At least I don't go to other people's lectures. So just from feedback I've gotten over the past 2 years, I do things a little bit differently. I do not follow the books quite, you know, closely at all. So over the physio lectures, you'll kind of notice that it's not necessarily in line with the books. I'm not here to read off what you can read at home. I'm not here to just regurgitate what you might have already read. Coming into the class, mine's definitely more laid back. This lecture I give, it's different every time. It really just depends on you guys. So the beginning of every lecture, I have slides that say what you need to know. And we'll get over that. We'll get into that shortly. But that is stuff I pull straight from AAMC. It's the fundamental information that you need to going into the exam. So if you noticed, I'm sure I think Todd's email said you guys are 3 weeks into this course. The books are in excruciating detail. It is so painful. And I have designed these lectures. You have the PDFs. So I'm sending them out one more time. The PDF is just designed for, when you get to January, assuming you're taking it in January, and you just want to review all the different physiological systems. You don't really have to go back and read through that textbook in painful detail. I have, just the fundamentals you need to know here in this lecture. So this lecture also kind of doubles as a study guide for you. So for physio, what it is you get all this, fundamental information, and you'll see what it is in the first two slides. And it's how do we build on from that? How do you take information from OChem? How do you take information from physics, maybe biochemistry, integrate it in? And it's really just taking this information and building up. And so as we go through the lectures today, if you guys have any diseases that that are relevant, just shoot them out. I love going into tangents. I love talking about clinical scenarios, clinical cases, because that's what the passages are going to be. You're not going to be just asked just raw, hey, what is an action potential, which is the electrical impulse. It'll be more of, we have this case study, you have this experiment, it's how we kind of apply it. And so I love talking about this tangents. How do we build up from that? How do we take this information and apply it to a patient? So in terms of just office hours, I don't have a set office hours. I more or less function as a virtual open door policy. You guys can just send me an email at any time, and we can I can communicate via email, or we could do more one-on-one office hours. Feedback that's been a lot more helpful in the past. Usually when we have giant office hours in the middle of a week that has 20 to 30 people, not everybody gets the most out of it. So if you have any questions, you want to set up office hours, just email me and we can make that happen. If I get inundated with dozens of emails, I will organize something more so for bigger group. But if it's just a handful of people, I'll try to fit them all in one-on-one thing. My schedule's a bit strange, so it's never the same time every week. I work 3 jobs currently, so it's really just a balancing act. And so I will work with you to find a time when we're both free. There's a question. Do you suggest study just the notes rather than the TBR, since my follow AAMC and TBR is too detailed? If you're short on time, I know, but you're 3 weeks in, phase 3s are coming up, you're probably already behind. That's completely normal. But if you get way too behind, way too bogged down, I'd say, yeah, look at these, get that the fundamentals down, and practice tests. So practice tests, I think, are huge. Learning how to take this information and kind of apply it. If there's so much random nitty-gritty detail in that book that if you just don't have the time, I would say go over this. I'm not saying the books are useless. It goes into much more detail and makes your kind of your background a little bit more robust. But this is just how I outline it so that you guys do have a study guide later on down the road. Any questions? Anything I might have forgot? Can you see my screen? Making sure I'm not having any difficulties there. Cool, cool. My email, just in case, let's see. My background is, there's a question. Yeah, so I graduated from UC Irvine in 2020. Let's see. Yeah, I've been working in the clinical setting for about almost 6 years now. So a lot of uh, experience in building off clinical case scenarios. Um, I've been doing TBR for 2 years. I'm actually applying to medical school right now, and it's early in the process. So at this point, not a flex. I'm not trying to do that to you guys. At this point, it's 10 interviews and 5 acceptances. So if you guys, this is also another thing. If you guys just want to talk about life, um, feel free to set up office hours. You could talk. If you guys want to talk about your application, I would love to discuss that with you. And so, yeah. I'm here for you guys. Open door, you know. So whatever. Uh, Tell us your score. I don't know about that. Uh, Above 90th percentile, but yeah, um, that's all you need to know. I did. I did take TBR. I took TBR when it was in person back in 2019. Well, I had Todd in person. I don't know if you guys have met Todd too much. I know he's taken a step back more so for this course. Todd is a godsend. He is the best. I love that man. I would take a bullet for Todd. So, you guys, I don't know if he does office hours, but just kind of talking to him, he just makes you feel special, He's one of those people. Okay. So yeah, if you guys just want to talk about life, let's say you got something bothering you, if you want to talk about just MCAT, not necessarily content, just more of, how to handle it. If you guys are still in undergrad, talk about classes and the process, I'd love to talk. Yeah. Uh, let's see. I will resend the slides. Yeah, they should be in the chat. Let's see. So I'll be here for all the physics every Saturday. You'll spend your weekends with me. Hopefully you guys enjoy it. And it really is what you make of it. I know this last summer, they really, really liked going on tangents and talking about clinical cases. So what's the trend of IRL versus online lectures? How the scores? I don't think necessarily the trend versus in person versus online has changed that much. I definitely know that I've done a lot more office hours online than ever did in person, just because it's easier for people to meet up midweek online than it is in person. So I think I've been able to, with certain people, dive down deeper than I would have had done previously. Then, I mean, also online, I feel like these lectures have become a little bit more enjoyable because you don't necessarily have the fear of asking questions. Just because we're hiding behind a screen, people will send more in the chat. And so I feel like that's kind of enriched physio for me a little bit more. People want to be a little bit more inquisitive, a little bit more curious. And so I don't think there's too much of a difference. I know I've heard you guys definitely are more on the collaborative side than previous online classes. In person, we were super collaborative because we got to work together. But yeah, let's see. I am located currently in Orange County in California, so it is still the morning for me. Yeah. So I do work tonight. I work at the Honda Center in Anaheim, California, and it's a George Lopez comedy show tonight. So I'm EMT for that. So that's pretty cool. So got a lot of that type of stories. Speaking of nervous system, I had a patient 2 days ago that we had a cervical spine fracture and was paralyzed from the neck down. So that's kind of I could talk about clinical cases like that. Let's see. Did I hunker down in Northern California for my TBR session? I did not. We had a TBR in Orange County as well. But I am from Northern California originally. Yeah. So there was originally locations all up and down California for TBR, not just in Berkeley. Kind of misleading. But I've had people for online, people from India, people from China, all around the world. So that opens up access to a lot of people as well. Okay, let's see. Yeah, make sure I'm not missing anything in the chat that I need to address. Alrighty, 41 people. Very cool. Usually we break these up into more sections. And so during the summer, we had 3 sessions of about 20 to 30 people. Okay, let's get going. All right. This one I don't think is one of my longer lectures. I try to keep things on time for you guys. There's a couple lectures in the coming weeks where I just kind of geek out and nerd out, and so we will go over time, but I think today we should be able to go. So any questions? Everyone has the PDF. I hope you're able to open it. If not, let me know. If you can't hear me, again, let me know. If I, for some reason, start going too fast for you, you can send it in the chat. You can private message me if you don't feel comfortable saying it in front of everyone. But yeah, sometimes I'll speed up. So just tell me to slow down if needed. All righty. So as I said, what you need to know, so these are the lists from the AMC website. When I was studying, this is what I used because I got behind real quick and did not want to read. And I'm not a really big reader, so the book was a little bit not for me, which is fine. That's just how I study. I know how I study. So I use this list. And so that's kind of how I built these lectures. So what we're going to need to know is the structure of a nerve cell. So we're going to go over just the basic structure, the major functions of the nervous system, the organization of the vertebrate nervous system. So we're not needing to talk about invertebrates. We're not going to talk about the jellyfish neural net. We're going to look at the difference between sensor and effector neurons, so the sensory versus motor neurons. Of the autonomic nervous system, the branches of the sympathetic and parasympathetic system. We're going to take just a quick gander at a reflex arc and see how we get some level of processing at the spinal cord. And we're going to take a brief gander as well as integration with the endocrine system. So we do have the endocrine lecture, which is, I think, the very last bio lecture. That is the most dense, the most memorization heavy of the physio lectures. I'm not huge on memorization, and definitely let's talk conceptual and learn how to take these building blocks and build upwards rather than brute memorization. Not a fan of that. You have too much to memorize already. Of that nerve cell, the different parts, the cell body, also called the soma, the dendrites that are called the dendritic arbor, the axon, the synapse or the gap between the two neurons. And we're going to talk about action potentials and resting potentials, the electrical properties of these cells, how an electrical signal gets sent from axon, well, down to the axon and from neuron to neuron, and how we do have excitatory signals and inhibitory signals. So that's about it. So it doesn't seem too daunting. I mean, I don't know, I haven't actually read the book, but previous sections which I have read, I'm sure this section was a lot more disgusting. So don't want that. All right, so nervous system structure and characteristics. So as I said, you said, dude, like 60, is it really 60 pages? I am so sorry. Good Lord. Alrighty. Organization of the vertebrate nervous system. As I said, MCAT is for doctor school. Doctors, we do vertebrate nervous system. We're not talking about the invertebrate nervous system. It is highly organized and split into the top level of organization, split into two categories: the central nervous system and the peripheral nervous system. So the central nervous system is the brain and spinal cord. Everything else, all other nerves, are part of the peripheral nervous system. And that gets broken down into a lot more subcategories. So in the peripheral nervous system, we have motor versus sensory neurons. Sensory neurons do exactly what they say. They sense your environment. And so what they do is they take information from your environment, bring it back to the central nervous system for processing so that you can actually make sense of it. The motor neurons go to your muscles and glands, so they help you move. Their glands, they can cause contractions to make secretions. The motor neurons can be broken down into the somatic nervous system, so the motor neurons and muscles you can control, and the autonomic nervous system, things that you don't control, which are the sympathetic and parasympathetic nervous system. So the fight or flight and rest or digest. So we're gonna actually break down and go into each of these throughout today. Do I have PDFs of the bio book? I do not have PDFs of the bio book, unfortunately. So yeah, I just have PDFs of the slide, and that's, I think, all you need for today, especially if this section was 60 pages long. Alrighty, so let's look more at the central nervous system. So, right, brain, spinal cord. So I think in one of the psychosocial lectures, we talk about the diencephalon, mesencephalon. It may even talk about it in the book for this. I've never actually encountered that on an MCAT test, MCAT practice test or whatnot. Just the big structures of the brain that I do want you to know are the thalamus. So we're going to go down each of the ones I want you to just be able to recognize off the top of your head. So the thalamus, this is the most primitive brain structure. Any organism that has a brain has a thalamus. So this is where a lot of the integration comes in. So yeah, sight, temperature, everything goes to the thalamus, and the thalamus sends it up to the cerebral cortex. And so the cerebral cortex is this fun area right in here. So cerebral cortex is where higher level processing comes in. So we have a giant cerebral cortex. That's what makes us so smart. If you look at more primitive creatures, they have smaller cerebral cortices, but everyone has a thalamus. So the thalamus is that most ancient, most primitive brain structure, and we've evolved from there. Is smell the only sense that isn't processed through the thalamus first? I actually don't know where smell is processed first. But yeah, just rule of thumb for MCAT, everything goes to the thalamus first. I don't know if anybody knows off the top of the head where smell's processed first. It's definitely in the. What's the main thing to know about the thalamus? Oh, all the information, your sensory information is going to go right to the thalamus, and the thalamus will send it up to the cerebral cortex for higher level processing. So you have several different visual processing centers in the cerebral cortex. You just get raw information to the thalamus. The thalamus can't tell you diddly squat, but when you sends it out to different areas of the cerebral cortex, that's where you get picture. So you get color, you get movement, you see borders. Yeah. Pretty sure cranial nerves for smell go straight to the cortex. They might. So there are cranial nerves, 12 cranial nerves. You don't need to know the specific cranial nerves. I think smell might be cranial nerve 3 or it's one of the first 2 cranial nerves. You don't need to know those. You don't need to memorize them. Let's see. Pretty much the thalamus is the information relay center. You do have the hypothalamus, is where we'll talk about that at the very end, is where is it? You do have the nervous system information comes into your brain, and that is where you have the crossover between the nervous system and the endocrine system. So your hormonal pathways, hormonal signals. We'll touch on it briefly at the very end of today, but we'll definitely kind of flesh that out in the endocrine lecture. It's really cool stuff. So yeah, thalamus, essentially the brain relay center. Hypothalamus controls hunger and thirst. Off the top of your head, right? Hypothalamus, the H and the T, hunger and thirst. This is where the brain really overlaps with the endocrine system. So where it sends out all those hormones. The pituitary is that master endocrine gland. So when the hypothalamus wants to, send signals hormonally, it will send a signal to the pituitary, and the pituitary will relay something out. And what those hormones are, what each of those hormones do, we'll talk about in the endocrine lecture. The medulla is another structure that you need to be familiar with. It controls your heartbeat and your breathing. So it controls your heart rate, controls your breathing. Right now, you're sitting there, you're not really thinking about your heart rate, you're not really thinking about your breathing. You can control your breathing, but that medulla is setting the pace for you. It is controlling it for you. The spinal cord, we'll take a little gander at. Next slide. The cerebellum is this tiny little structure down in here, and that's going to control more of your fine motor skills. So there are people who will have cerebellar strokes, where they have a stroke in the cerebellum. What that does is that impairs movement. They'll have impaired gait, meaning that their motor skills and their walking will be a little bit impaired. Controls balance. If we actively control breathing, is the medulla autonomous or voluntary? So you can override the medulla. The medulla is autonomous. So when you're thinking about, hey, let's speed up my breathing, let's slow down my breathing. You will talk about more of what muscles are involved in breathing next week, but it's like we can tell our intercostal muscles, tell our diaphragm to contract and relax, and we can speed up our breathing. But when you're working out and you're building up that lactic acid, the medulla is like, hey, this blood's a little bit too acidic. Let's speed it up. Let's make it more basic. And we'll talk about how the rate of breathing changes the pH of the blood. And so when things you can't control, it will take over. It is more autonomic. You can't control your heartbeat either. You can't control your heart rate. You can't say speed up. It doesn't work that way. The voluntary aspect of that is in the intercostals and diaphragm. Would the switch from voluntary to involuntary breathing be a derivation of sensory adaptation, where the autonomic portion takes over after a while? Yeah, when it really comes down to it, the autonomic system will take over. So if you ever hyperventilate, and you ever think like, hey, I'm feeling a little bit dizzy, I'm feeling a bit woozy, and you pass out. So what's happening is when you're hyperventilating, you're getting too basic of blood. You're blowing off too much carbon dioxide, and your medulla doesn't like that. Your brain doesn't like that, and so it's going to tell you to pass out so that it can take over. So end all be all, your medulla will take over. It'll take you out of the driver's seat if it needs to. Okay, the amygdala linked to emotion. So people sometimes have an overactive amygdala. Overactive amygdala can lead to OCD. It can lead to anxiety. I know right now, probably all of us here are a little bit anxious. Our amygdala is kind of overactive a little bit too much. They got MCAT setting to do, a little bit stressed. Hippocampus linked to memory. Make sure you get good night's sleeps during the study. Let memory be encoded in the hippocampus. And for the brain, these are all the structures. You don't really need to worry about reticular formation and whatnot or anything. Sleep is for the weak. Oh boy, definitely not. I'm a huge sleep nerd. That is a tangent for a later time. Sleep is the best thing you could do for yourself right now. I make sure I get 8 hours of sleep per night, and it is the best thing. If you sleep less than 7 hours per week, or per night, the next day, your immune system is about 70% reduced. So Yeah, so get sleep. Get the sleep schedule on track, guys. I promise you'll feel the difference. You will feel the difference. All right, let's keep going forward. Let's clear off the annotations. We might go longer, and I apologize. Okay, spinal cord. So this is the other structure of the central nervous system, highly organized. We see blue lines here and red lines, and we'll talk about that a little later on. These are different parasympathetic and sympathetic nerve origins. But as you see, the nerves that go down to all your organs, they're coming branching off the spinal cord. And when you get sensory neurons that go back to your spinal cord, you'll get, small level processing here. And it'll process if it needs to really quick and create a response before it sends it up to the brain. So you really don't need to know the spinal cord tracks. There are different tracks that go from the spinal cord up to the brain, and vice versa. You guys don't need to know that. Just know, like, hey, here's the spinal cord. This is where it's highly organized. We'll kind of look a little bit deeper at the organization later on. But yeah, this is spinal cord. Let's see. How do we get a good sleep schedule when we are behind in class? Discipline. I know at a certain time at 10, just say, hey, I'm going to bed. And yeah, I know it's a little bit rough that you always have more to study. You'll always have more to study, but just make sure that you get that good night's sleep. So the studying you do does get encoded into your memory, does go to that hippocampus, right? And then make sure you're getting a good night's sleep so that you can be productive the next day. I am a sleep junkie. And it's not like I sleep my days away. I don't nap during the day. That's a no-go. It's 8 hours or more per night. So yeah. The structure of the neuron. So briefly kind of mentioned all the different structures in the first two slides. We start off in the dendrites, also called the dendritic arbor. Why is it called the dendritic arbor? Because it looks like a tree branch, right? It all has tree branches. And you'll have hundreds of different neurons sending signals to this neuron's dendrites. So the signals from all other, different pathways, they converge on this neuron and they send it to the dendrites. So you can get excitatory and inhibitory signals here. We'll kind of look at that in a few slides as well. Those inhibitory and excitatory signals will travel down the dendrites and will go to the cell body, also called the soma. And we'll get some processing here at the axon hillock. So the very start where the axon, or this giant highway that will have the net impulse, that nerve impulse, that signal propagation. When we get to this area where that highway meets the cell body, you have this axon hillock, and it will kind of process the strength of that signal. If that signal is strong enough, it will send a full on impulse. And the impulse is called an action potential. We'll cover that shortly. We are covered in myelin sheath, which allows for insulation of this, essentially a wire. So, you have these wires, you have the insulation around it. Myelin sheath protect the nerve, they protect the neurons. It insulates it, it speeds up the signal. So it's something that myelin does, not only does it protect, but it speeds up signaling. So when you do have, muscle memory or, very important neurons, they'll be covered in myelin sheath so that these nerve impulses can fire quicker and quicker and quicker. And what creates the myelin sheath are the Schwann cells in the peripheral nervous system, or oligodendrocytes in the central nervous system. They're both called myelin sheath, but the type of cell that creates that myelin sheath is a bit different. We'll take a quick little gander at the Schwann cells next slide. But after we reach that axon and we go through that, we enter the end of our wire, so to speak. And the end of it's called the axon terminal or the terminal boutons. You might see both given in a passage. You don't need to know the different nerve tracts. No, you do not. Think of the spinal cord. Thank the Lord. But all these things, like, they might talk about a nerve tract in a passage, but the information that is not on these two slides up here, that will be given in the passage. So it's how do you take this information and integrate it with the information they give you in the passage. That's why it gets so hard, is they start throwing jargon at you left and right. It's how do you through practice tests, you'll learn the patterns. What information is important? How do I take that and integrate it with what I know to build up and find my answer? If can neurons develop myelin sheath over time if found necessary? Absolutely, they can. And so that's one of the things with muscle memory. And you do the same thing over and over and over and over again. The those motor neurons and those nerve pathways, they can grow myelin, and so that's why you get better and better with time as you have more. Um, you have quicker impulses. Sometimes you can have, if you don't have myelin sheath, you can have crosstalk between neurons. Sometimes one electric pulse through one neuron can accidentally fire off another one. That's very rare, but it can happen in some diseases like multiple sclerosis. So do neurons have directionality? They do have directionality, and we will discuss that shortly. Um, so this is the myelin. This is a different kind of depiction of that myelin sheath. So we have those Schwann cells, which are these guys wrapping our wire. So the Schwann cell does not only attaches, but then wraps itself around and around and around, creates this very, very tight insulation. As you can see, it's wrapping around over and over and over and over again. And pretty much all the cytosol and all the cytoplasm has been squished out to the outside layer. So you just have cell membrane. So you have this phospholipid bilayer wrapped around in layers and layers and layers. It's great insulation. Now you can have diseases that affect the myelin sheath. Can anybody think of a disease that can affect the myelin specifically? MS. Awesome. Very, very much so. Multiple sclerosis, autoimmune disease where we attack the myelin sheath, we destroy it, and that causes crosstalk, impaired motor function, and it goes on and on over time. And so you do to kind of counteract that type of thing. You can take long courses of high dose steroids. There are immunotherapies now, but yeah, it's MS, autoimmune disease that attacks the myelin sheath. ALS, oh gosh, ALS, also called Lou Gehrig's disease. I actually don't know the mechanism of ALS, but it is a progressive. I think it's a more neurodegenerative, and not. I don't know if it's autoimmune per se, but that might be also a myelin sheath disorder. I can't confirm for sure. Parkinson's is not a myelin sheath one. I can talk about that in a sec. There's a question that I missed up here. Schwann cells are just for the peripheral nervous system. Yes, but we do in the central nervous system. We still do have myelin sheath, but it's done by the oligodendrocytes. It's a different type of cell, but it does do this essentially the same thing. Parkinson's is a disease where the dopaminergic producing neurons, the dopaminergic center becomes a little bit underactive. And so we have levodopa and carbidopa, different dopamine replacements that can help with Parkinson's. But yeah, so it's just more of a dopamine deficiency. And we have some neurotransmitters here in about 7 slides. Got it. So ALS is a neurodegenerative disorder that does do demyelination. Cool. But it's not autoimmune. So there's also another one that's very similar. Oh Lord, what's it called? Oh, there is, it kind of presents the same way as ALS for the most part, but it's not as lethal because ALS is definitely more systemic, but there is a kind of motor disorder kind of like that where the more you use your muscles, the more they degenerate because you don't have the stem cells to replace them. Um, yeah. Yes, Duchenne muscular dystrophy. Thank you, DMD. And then Michael, what is ALD? I don't know that one off the top of my head. I've never heard of that one. I'm gonna take a screenshot and I'm going to look at that one. I haven't actually seen that. Very cool. Take a screenshot. I'll look at that one. Yeah, if you guys want to look at that one too, maybe very interesting. DMD is not demyelination. It kind of presents similar ways, but that's more of a, you don't have the stem cells available to kind of replace the muscles when you break it down. So as you use it, and you can't rebuild muscle, and so over time, it really presents. You start to see symptoms around age 15 or so, but is Duchenne muscular dystrophy. But that is not a demyelination, but it kind of looks like it. So there's different mechanisms of ways that we can get to very similar diseases. But yeah, at the end of, yes, I did skip the nodes of Ranvier. So the nodes of Ranvier, as we see here, are the gaps between the myelin. And those are important because that's where the nerve does get, that's where the signal does get propagated on these myelinated axons. So when we do have a signal that starts over in this area, so if I go back one slide, it starts over here, where we have the openings of these gated channels, we don't have them, the channels that we're going to talk about here shortly, don't open where there's myelin. They open where there's not myelin. So the signal kind of bounces from gap. And that helps speed it up. So that's what the nodes of Ranvier are. So the nodes of Ranvier are where these gaps open up. Are the nodes of Ranvier exposed part? That's exactly what they are. The exposed parts of the axon in between the Schwann cells. Awesome. We'll get into what the action potential looks like as it travels through the axon. Haven't quite got there yet. We're almost there. But as that action potential, as that electrical impulse does reach the end of our neuron, we reach the terminal boutons, and there's no direct electrical signal that hops from one neuron to another. We have the synapse, and we'll kind of circle back around to the synapse in a few slides here. But as this electrical impulse gets down, it opens up different types of channels at the end, and we release a chemical into the synapse. And this chemical, called a neurotransmitter, will cause an excitatory or inhibitory signal to the next neuron. All right. Let's actually look at what the action potential looks like. How are we having any sort of electrical properties on these cells, right? Electrical properties, think electrocution, that sounds very dangerous, but we do have this electrical propagation throughout our bodies all the time. You being here, you have a ton of electrical activity going in your brain, going to your diaphragm to make you breathe, going to your heart to keep that pumping. So what it actually looks like, this is a resting neuron. Let's start, just electrical properties here, and we'll see why there's electrical properties. We'll look at how to calculate that here in a few slides as well. But at the resting potential, let's say just a neuron just sitting there chilling, doing nothing. Its membrane has an electrical potential of negative 70 millivolts. What electrical potential is, you'll talk about it in physics, but it's more of like essentially the electrical version of potential energy. It's the electrical energy available to do work. And so at resting, we're at about negative 70 millivolts in mammals at 37 degrees Celsius. What happens is we get these signals that come from the dendrites. And these dendrites will allow different types of ions to flow through. We might get chloride rushing in. We might get sodium rushing in at these dendrites. And it will be calculated, it will be added up at the axon hillock. And we'll take a look next slide. But as these signals are calculated at the axon hillock, you'll slightly change the membrane potential at the axon hillock. So we might get a small little change, nothing's going to happen. We might get a little bit of a bigger change, nothing's going to happen. But let's say we get this big change in electrical potential. We have different types of ions that are flowing through from our dendrites to our cell body and are accumulating at the axon hillock. And let's say now the electrical properties of the membrane at the axon hillock change to about negative 50 millivolts. So we've gone from negative 70 to negative 50 millivolts. And we'll talk about why it's specifically negative 70 at resting in a few slides here. But we get to that around negative 50 millivolts, and you reach this threshold potential. It's this all or nothing threshold that if we break it at all, if we surpass it at all, we will get an action potential. We will get a full-on electrical propagation, and it will essentially depolarize. And the reason why it's called depolarization is because we're heading toward zero. So being at negative 50 or being at positive 50, you are polarized to one side or another. We're negatively polarized here. So we're getting a depolarization as the membrane's electrical potential starts heading towards zero. It surpasses it a bit, and then it's going to try to repolarize itself. It's going to try to go back to where we were. And so this little depolarization and repolarization of our membrane is that electrical signal. It's that action potential. And so the type of neuron, how many action potentials, the frequency of action potentials, all those kind of categories brought together can give information to the very next neuron on what type of signal it's sending, what type of downstream effect it has. There's a question, what is depolarizing the resting potential to the... Yeah, so we're going to get that shortly. So what is depolarizing the resting potential to that threshold if sodium channels are closed before reaching that threshold? And so that's where the signals, the excitatory and inhibitory postsynaptic potentials are coming in, and I have that on the next slide. But for right now, let's say we are at the axon hillock, and we do have a depolarization. The electrical properties of that membrane changed enough to hit that threshold. What's going to happen is downstream, now at the beginning of this axon, the sodium channels, these voltage gated, they're voltage gated because we're having a change in electrical property. The voltage gated sodium channels will open up. So they're going to open up and they're going to flood these positive sodium ions into the cytosol of this axon. So that's also going to change the electrical properties of the membrane in this area. And as these guys start flowing to the right, the membrane here is going to be like, oh, wait, my electrical properties have changed. So these guys are going to open up. And so as we go down, so these guys are now going to open up. And the sodium is going to rush in to this one. And it's going to open up these guys, and so on and so forth. It's going to continue traveling in one direction. But behind it, to balance out, it's like, okay, we have this giant accumulation of these positive potassium ions on the inside, and these positive sodium ions that were on the outside, they come in, the potassium behind it's going to flow out. And we'll kind of look at what channels open up when in a couple slides here. But as an action potential goes through, the sodium rushes in, potassium rushes out, and we kind of have this refractory period where now that this guy's opening up, we're still in this period of potassium flowing out. The sodium channels that were just opened are going to be closed for a brief time. And what this does, that's going to give a directionality. It's not, even though these guys are flowing in and it's diffusing to the left and diffusing to the right here, when the ones that diffuse to the left aren't going to actually trigger any action potential, because we're going to have a refractory period there. That area of the membrane isn't going to be able to respond to that stimulus. Yeah, and so let's say an action potential just went down this axon. So now we have a dilemma. We have a lot of sodium on the inside, a lot of potassium on the outside. Well, that's not what resting state is. That itself will change the electrical properties of the membrane. And so to reestablish that resting potential, you will have these sodium potassium ATPases. It'll take energy. We will shuttle 3 sodiums back to the outside and 2 potassiums back to the inside, and we will try to reestablish that resting potential. So that is a sodium potassium ATPase, but these voltage gated channels And so there's different types of channels. We'll talk about ligand gated in the endocrine lecture, but these guys are voltage gated channels. That voltage change is going to trigger them to open and cause an influx or efflux of these ions. And so as we see here, we have these nodes of Ranvier, and we have this myelin sheath where the voltage gated channels aren't opening here. What's happening is that signal, the impulse is bouncing. It's bouncing and speeding up along that axon. And so what's happening as we do have hyperpolarization of, we're trying to repolarize back, that sodium potassium pump will bring it back to resting potential. So you learned salty banana, neuron wants more potassium inside than sodium. I've never heard that one. I do like that. Yeah. So if you ever are stressed out in the MCAT and freaking out because you don't know which is on the outside, which is on the inside, I just learned a new one. I'm going to use that. So thank you, salty banana. Yep. More potassium on the inside. Na has 3. Whoa. That's a cool one too. Pumpkin. Whoa, that's cool too. Oh, wow. You guys are fun. I like this. I like your guys' mnemonics. I appreciate them. Okay, so there was a question. Darn it, I just accidentally annotated this. There was a question on how do we get the voltage to change at the axon hillock. So we get these signals from the dendrites. So we have 2 different types of signals we can grab. These dendrites have multiple neurons signaling to them. So we have excitatory ones and we have inhibitory ones. So it depends on which neurotransmitter these excitatory and inhibitory neurons are actually firing out. And what this does is that allows different types of ions to flow in. If it's excitatory, let's say these blue guys are excitatory, what they're going to do is they're going to, this neurotransmitter is going to allow sodium to rush in. So sodium's going to go to the dendrites. Sodium's coming from these guys. So we're having some voltage change in these dendrites over here, and it's going to travel to the cell body, and it's going to accumulate at the axon hillock. If it's strong enough, it will signal an action potential. And so at all given times, we can have excitatory and we can have inhibitory, and they'll be added up. So it's summative. And so all these different signals are summative. So we have excitatory, another excitatory. Oh, we have an inhibitory one. It's like, oh, we have a break here. There's no signal. It's like, oh, we have another excitatory that comes in, another inhibitory, and a big excitatory. Hits that action potential threshold, you're going to hit the all or nothing response. You're either going to get the full action potential or you're not. So you're actually going to hit up and go down. Ignore that negative 10 millivolts there. But they are summative. So IPSPs and EPSPs are graded potential. So why are they called EPSPs, IPSP? So it's excitatory postsynaptic potential. This is the synapse right here where they meet. And so this excitatory effect is going to be a postsynaptic potential because it is after that synapse. Yeah, so you can have sodium influx that causes EPSPs excitatory. You can have chloride influx, which is another one that is outside that can cause an inhibitory. And so they're graded. The strength does matter here. They add, so not all EPSPs are created equal. Not all IPSPs are created equal. And so you can just add them all up. But once you do hit that threshold, you will get an all or nothing. So you can't get a stronger action potential than another unless you change the actual properties of the nerve cell itself. You can artificially do that, but for the purpose of the MCAT, all action potentials are created equal, all or nothing response. Alrighty, so we do have another slide that does show directionality. AP is all or nothing action potential. So AP is an action potential. Correct. That is what it stands for. I just saw that. Cool. So we do have directionality, right? We're getting that rather from that soma. We meet at the axon hillock. We do get a depolarization. So it gets depolarized, diffuses to the right, and as where it just was, it's going to be repolarizing. So it can't go backwards. It can't go in that direction. So there's a directionality to this. Now, there are instances where you can mess with that. So if you signal, let's say we have some artificial or exogenous electrical stimulation of the membrane right here, and we depolarize this first, and let's ignore this depolarization here. And as it diffuses to the left and diffuses to the right, you can get action potentials going in both directions. And the reason why is because this area wasn't repolarized. We weren't in that refractory period. It's at time zero, we stimulated in the center, so we can go in both directions. And this is where you have things like MS that cause issues, because as that myelin's getting destroyed, and you have a neuron that's sitting on top of this neuron, as this one is depolarizing, you might accidentally change the electrical properties around this one and cause ba-bam, action potential, ba-bam, action potential, crosstalk. And so there are, as your anecdotal like hypotheses that in the brain, autism has a little bit of crosstalk. We'll kind of go back into autism in the GI lecture. That sounds very, very random, but trust me, it's an interesting tangent I want to go on. So that is a little treat for a later day. So when we do have these action potentials, what do the voltage gated channels look like? Well, at rest, so at the top one, we are at rest. Everything's closed except potassium leak channels. So potassium leak channels, they're going to come into play in a couple slides when we talk about why there is a resting voltage potential and why it's negative 70. But let's say we do have this signal that comes in, and there is now this change in membrane potential. It's now past the threshold. As we head up through that action potential, these potassium leak channels will still be open, but now we do have these voltage gated sodium channels that are opening. And as those open, that's going to change the electrical properties. And we'll talk about why it changes the electrical properties. And that's going to depolarize it. It's going to send it toward the resting potential of the sodium. Then we get to the top, those sodium channels close, potassium channels open up, and we're going to repolarize back to rest. And so potassium is going to flow out. Yeah, so we do have, I'm going to go back to the slide previous to this one. But as we do have resting, everything's closed. So potassium leak channels are open. They're leak channels. They're always going to be open. But we have the electrical impulse. Sodium channels open up. Then they close. We do have the refractory period. Potassium channels open up. Potassium flows out. And then after we reach this area, as we repolarize, we'll have that sodium, potassium, ATPase trying to reestablish that resting potential for us. So if we go back and kind of try to let's superimpose those sodium channels onto this one. We have these sodium channels that open up, and the positive ions flow in. And then once it has depolarized, it's going to open up these sodium channels. The potassium channels here are opening up, so it's repolarizing. Why do we need two potassium channels? So we do have the potassium leak channels, and we'll see electrical properties, why those potassium channels do play a role. We'll see that. Let's see, there's another one. What happens in the refractory period? So the refractory period, what happens is, it doesn't really show it here, but there is a little kind of appendage that can go in and block this off. And so no sodium channels, no sodium ions can even flow through to even cause an action potential. This guy closes up and potassium channels are opening up. So potassium channels opening up, this guy is being blocked off. In a refractory period, we can't possibly send a action potential back to the left. So it's a refractory period. It's a ball and chain. Yeah, that's why I drew a little ball and chain. So yeah. So potassium does not flow in at that time. Potassium is flowing out. So potassium is still flowing out at that time. And so that's going to hyperpolarize it. So we'll talk about why that's going to hyperpolarize it on an electrical property level here shortly. But then when we get to this point, these guys are both going to close. Once these guys both close, we'll have the sodium, potassium, ATPase shuttle them back into where they need to be. That salty banana, more potassium on the inside, salt on the outside. Can a refractory period help bring us to the resting potential, or does the impulse always send that point? It does help us to resting potential to some extent because it's preventing more sodium from even flowing in. Yeah, it's not explicitly. That's not the point of the refractory period. The refractory period was evolutionarily developed, selected for, so that you only have one direction going, only one direction action potential. Alrighty. Okay, so when we did talk about neurotransmitters here shortly, briefly, when that action potential reaches the end, so we're still talking about this change in that membrane voltage. The action potential is going down and it's traveling, hits the axon terminal, the terminal boutons. Let's add in another type of voltage gated channel. We now have voltage gated calcium channel. Calcium is very unique. So what calcium does is it's not going to cause any depolarization. It's not causing any hyperpolarization. Those are still the sodiums and the potassiums. What's happening is the calcium channels will open up this due to a voltage, right? They're voltage gated, so it needs that action potential. The calcium will rush into the cell here, into the terminal boutons. It will bind to these vesicles. And when it binds to these vesicles, we have these little snare proteins on the inside that will grab on, they'll latch on to this vesicle, pull it down. This vesicle is just a little package of chemicals. It's a little, happy little gift. The snare proteins are going to pull this little package of chemicals to the cell membrane surface, and the vesicle will fuse and release chemicals into this space. And those chemicals are neurotransmitters. And what these neurotransmitters are do is they'll come in to ligand-gated channels. And we'll talk about ligand-gated channels in a future lecture. It'll bind to these channels and allow an influx of this chloride, allow the influx of a sodium, and cause these either IPSPs or EPSPs. And the type of neurotransmitter, the type of location where it is, the type of neuron, that's where it's going to cause issues. So in Parkinson's, we talked about that. That's a dopaminergic neuron. So the neurons that release dopamine into the brain, these specific areas, are basically becoming non-functional, atrophied, and so we're not releasing dopamine, and that causes the tremors. That's what's going to cause the Parkinson's. So once these neurotransmitters are in this synapse, also called the synaptic cleft, they're going to signal, but we don't want them to signal forever. I mean, we have times of happiness where we have the serotonin release, and we have times of sadness where we have this absence of serotonin. If we had serotonin all the time, we'd always be happy, and the reward centers, the brain, would be completely useless because we're always happy. We're not going to do anything. So we don't want these neurotransmitters to be in here forever. So there's different ways that we can get rid of them. You can have reuptake, where these neurotransmitters will be reuptake via this pump, placed, packaged back into a vesicle, into a happy little package. That's one method, reuptake. There is enzymatic degradation, where you have enzymes that come in and start to degrade these neurotransmitters. And then you just have diffusion, where they just diffuse out and become so, diffuse, not very concentrated, that doesn't really cause any downstream effects. So there's the three ways we clear out neurotransmitters is by reuptake, enzymatic degradation, or diffusion. So we can actually hijack this pathway. So if we ever have depression, right, there are medications that can help. So what are these medications? There's two main classes. There's SSRIs and MAOIs. So an SSRI is a selective serotonin reuptake inhibitor. So what it does is it inhibits this pump, it inhibits this reuptake. And if it inhibits reuptake, it's going to keep serotonin in there longer. And so that's going to allow more happy signals to be sent. So then there's MAOIs. What's MAOI? It's monoamine oxidase inhibitor. So it's going to inhibit the enzymatic breakdown. And to inhibit an enzymatic breakdown is also a mechanism by which we can leave these chemicals in there, send happy signals. And sometimes some people tolerate SSRIs better, some people tolerate MAOIs better, some people need both. It really comes down to that. Couple questions here. With reuptake, do the vesicles with neurotransmitters just stay in the presynaptic? So yeah, those vesicles, these happy packages, when you reuptake them, they just sit here in this terminal boutons and they wait. They wait for that voltage to come through, open up those calcium channels, wait for the calcium to bind to them so that those little snares can bring them in. Reuptake, enzymatic degradation, and the last one, sorry, might be swallowing a few of my letters, diffusion. It's just going to diffuse out and spread and become super not concentrated. Any other questions on kind of the functioning of how we send a nerve signal? So it starts with that dendrite. The dendrite's going to pull in those IPSPs, those EPSPs. It's going to kind of sum them at the axon hillock. Then if we reach that threshold potential, we'll send that electrical impulse, we'll send that action potential. The action potential is going to travel all the way down to the terminal boutons, open up these calcium channels, and that's going to allow neurotransmitter to be released. Any questions at this point? Alrighty. So you'll learn about ketamine treatments working well for depression. I actually don't know much. Oh gosh, we give ketamine to sedate people. I take ketamine for headaches sometimes, which is very strange, I know. I don't know why ketamine works for depression, but I have heard that. And there was a study that just got released or just gaining some public attention that they have found that hallucinogenics are helping with depression. Hallucinogenics help with PTSD as well. That's doing something with the happiness centers. I read papers, but not usually neuro papers. So I'm not too up to date on that. I'll talk about my papers for all the other ones. But yeah, this one, honestly, it has the fewest tangents. So I apologize for future lectures. But yeah. How do chloride ions fit into action potentials? So chloride actually does the opposite here. Chloride, well, you will talk about the electrical properties in a couple slides. For the purpose of the MCAT, you don't need to know too much about what chloride does. Sometimes we do have chloride that sneaks in, but it's really just to balance out charges because we do have as you can see, we have a ton of positive charges in here. We don't want to be too positive. So it is present in varying concentrations. It is a negative ion, so that's going to balance that out to some extent as well. But because it is an ion, it does play a role, but not a huge role, and we'll kind of see why it doesn't play a huge role in a few. It does work in IPSPs. They can shoot IPSPs at the dendritic level because that's going to cause the opposite change. If we just have, let me get rid of this annotation. If we just have a bunch of IPSPs, what it's going to do, where does that slide? We have the IPSPs are going the opposite direction. So the change it has on the chemical properties of that membrane is it's going to turn it in the negative direction. So you can essentially, if you just have an absolute boatload of IPSPs, you can send the membrane potential even further negative. So that's why it is inhibitory. It's sending it away from the threshold potential, and you'll need more and more excitatory potentials to kind of override those. That's why it's inhibitory. Ketamine has shown to induce rapid depressive relieving effects by bypassing normal routes of activating glutamate. Oh, interesting. Okay. A neurotransmitter essential to keep away depression. Ketamine acts as a non-competitive. Interesting. Cool. What is glutamate? Fantastic question, right? So of the neurotransmitters, great little bridge there. Of the neurotransmitters you need to know, These are the guys. So obviously this PDF, if you don't have it already, let me know. But this PDF is just when you go through, it's a study guide for you. So we have the acetylcholine. Acetylcholine is a very, very, what's the word I'm looking for? Oh Lord, I'm blanking on the word. But it does a lot of different things. It can help with learning. It helps with muscle contraction. It is the parasympathetic neurotransmitter. Yeah. So where can you find this PDF? Yeah, no worries. I send it out. So if you're a little bit late, slowpoke, that's on you. But I'll send it out now. No worries. Um, yeah, so dopamine, movement, learning. So movement, right? If we have too low of dopamine, that's we're gonna get that Parkinson's, right? We're gonna get that essential tremors. So what we're going to do is we could take dopamine replacement therapy. So the dopamine replacement therapy with levodopa or L-dopa or carbidopa can help with those symptoms, but it's not really replenishing those dopaminergic neurons. It's just replacing the neurotransmitter itself. So you're watching the slide in your lecture. Yeah, so I will actually send them to you, but if for some reason you are watching on the phone, you can also email me and get the slides as well. That is not a problem. Serotonin is a mood neurotransmitter. It's going to make you happy. If you have a lot of serotonin, you'll be a happy camper. If you don't have a lot of serotonin, you will not be very happy. So norepinephrine is alertness and control. We'll talk about epinephrine and norepinephrine. Those are sympathetic nervous system neurotransmitters, fight or flight, running for your life, right? And then the two guys that really only exist in the central nervous system, GABA and glutamate. Those aren't going to be any of those peripheral nervous system guys. Those are just in your brain. GABA is the major inhibitory neurotransmitter, and then glutamate is, I guess, what ketamine is activating. It's a agonist. It's going to upregulate glutamate release. It is a stimulatory neurotransmitter. So all the neurotransmitters you need to know, just these guys. Dopamine, when we repeat what dopamine does, dopamine does help with mood, emotion, has some sort of learning effect as well. But the main thing that you guys need to know is influences movement for the most part too. And when you do have that undersupply of dopamine, when you have the dopaminergic or dopamine producing neurons that start to atrophy or become dysfunctional, you'll have Parkinson's disease. So the way Parkinson's is those dopaminergic neurons stop functioning. Cool. Going a little bit slow, but that is fine as long as you guys are enjoying what we're talking about. Cool. So what is the electrical property? So we got some math here. I'm not a math person by any means. I absolutely hate it. Good thing is you don't need to calculate anything. You don't need to calculate diddly squat. So the only thing here is conceptually, how do these equations work? There's two equations that you need to know for the MCAT for electrophysiology: the Nernst equation and the Goldman equation. So the Nernst equation is the resting potential for each individual ion. And it's calculated at a textbook value of 37 degrees in mammals. So just our typical homeostasis temperature. So what really goes into affecting the membrane potential for each individual ion? I'm not talking about the overall membrane potential. That's the Goldman equation, and we'll talk about that here shortly. But what is the electrical pressure? What's the available available energy to do some sort of work, to do some sort of change? How is that generated? So the first thing that comes into mind is the Z. So what is the Z? Z is the charge of the particle. So if we have potassium, it's a +1. Sodium, that's a +1. Chloride is a -1. So if we're dealing in this equation with potassium sodium, you can just get rid of that and it just becomes a +61 in front of the log. when you do have that chloride, let me back up, it's a -1, so it becomes -61 in front of this log. So the Z is, all it's doing is it's taking into consideration the charge of the particle. So and so if you can have, if it's a -2 ion, you'll plug in a -2 for Z. If it's a +2, like calcium, you'll plug in a +2 for Z and whatnot. There's a question. So Nernst's equation is the equilibrium potential per ion, not the resting equilibrium of the entire membrane. Yeah, so that is correct. Nernst is the resting potential of each individual ion on this membrane. And then we're going to combine them together for the Goldman equation. So where the magic happens in determining this value right here is that the ratio between the concentrations of the ions outside of the membrane, outside of the cell, and the concentrations inside. So let's look at potassium. So let's clear all this. Let's look at potassium. We go in, we have a +1. So we can pretty much ignore Z for this part. So the very beginning of this equation will be the electrical potential, or E, of the ion. So it'd be E, okay, right, equals 61, because it's a +1, right? Potassium is a positive ion. Log, so log math, absolutely a blast. Absolutely love log math. Sarcasm, I hate log math. So this is just conceptually, let's look at this. So salty banana, right? I'm going to use that one. That'll freaking love it. So salty banana, and where's potassium at rest? It's more, just say in the chat, how much potassium relative, where is it more, on the outside or the inside? Inside, cool. So we have a large number inside, small number outside. I'm not going to deal in specifics of concentrations. You can ignore that. You'll never be able to do that. We're just looking at this conceptually, right? So if we have a large number on the inside and a small number on the outside, this fraction is going to be less than 1. Just a fraction, right? If we have a big denominator, small numerator, the ratio, the value will be less than 1. So what's log of a ratio of less than 1? It's negative. I'm not even going to do the math. I don't have to do the actual log values. The log of a number less than 1 will be a negative value. So that's going to turn the resting potential of potassium into a negative value. So at 37 degrees Celsius in mammals, the specific actual values of the concentrations will come out to 87 when you actually plug it into a calculator, which again, you don't need to do. But conceptually look at this and like, oh, okay, that's why the resting potential of potassium is negative. If we look at sodium, I'm going to try to clear out that. If we look at sodium, again, that's a +1. Let's see, where's my drawing tool? There it is. If we look at sodium, again, it's a +1, so we don't need to change that. We have, oh, damn it, I didn't get that out of the way. We have very little on the inside, a lot on the outside. So the ratio of out versus in will be greater than 1. We have a larger numerator than we do denominator. The number's going to be greater than 1. A log of a number greater than 1 is positive. So if we look at this, this is a positive term. This is still a positive term. The resting potential of sodium is positive. Awesome. So let's look at chloride. Chloride is also, there's more on the outside than there is on the inside. So this term, because there's more on the outside and less on the inside, this term is also positive. However, chloride is a -1 charge. So this Z is a -1. So this negative term times this positive term will create a negative resting potential for chloride. So looking at these individual ions, does that make sense on why the directionality, just the signage? I'm just trying to get you to understand conceptually why the resting potential here is negatives for potassium, positive for sodium. There's more Cl on chloride on the outside. So that is why we have that right there. That is why this is a negative resting potential, because this term is positive. This term will be negative. So conceptually, hope that makes sense. I'm going to take this one step further now. If you have any questions, please ask before. So let's see. Directionality, what I'm meaning is relative to zero. So I mean the fact that potassium is negative, the fact that sodium is positive, chloride negative. That's what I mean by directionality. There's more Cl on the outside, correct? Let's see. So let me read a couple of these questions. So why does Z become negative or positive again? Z is the charge of the ion. So if we have a positive ion like potassium or sodium, Z will be positive. If you have a negative ion or anion like chloride, it'll be a negative charge. Let's see. There's a couple questions here. Would a +2 charge on the ion mean that Z is +2? Correct. Absolutely. How will this come up? There's a couple questions. Yeah, so I'll answer these as we go. How will this equation come up in a MCAT passage? So it's more of like, okay, we have the Nernst equation. Let's say it gives you some made up ion, or in this case, whatever it might be. Let's say we took out potassium and put in, oh gosh, something with a +2 charge. And then let's say this is the concentration out, this is the concentration in. You have to be able to plug it in. So say like 61, the Z will be a +2. So you need to divide that 61 by the 2. It'll be a positive number. And then just by comparing the concentrations of out versus in, which one's bigger, which one's smaller, and kind of putting that into a ratio and telling you, hey, is the log ratio less than or equal to 1? It'll tell you the sign, so the positive or the negative of that term. And so from there, you might have to try to predict the resting potential. So the choices might be positive because, well, A might be positive because, B might be negative because, C positive because, and then negative because. And so what you're going to look at is be able to first identify if it's a positive or negative resting potential for that ion, and then the reasoning why. So the conceptual reasons why. Then because if there's more on the outside than inside, or vice versa, whatever the situation, the current scenario would be. So this is more of a conceptual thing. You don't actually have to calculate the number. Thank the Lord. That's going to be negative. That's going to be terrible, right? Log math is disgusting. You might be given the Nernst equation. You might not. It's something that I do definitely recommend just being familiar with. So yeah, I've seen it where I have been given the Nernst equation before. I've also not been given the Nernst equation. It's also a physics equation. So because this is across any membrane, it doesn't have to be a biological membrane. So let's see. So these three voltages are what go into playing a role in determining the resting potential of a membrane, correct? So we'll get into that shortly. Just one other question. Does negative resting potential of that particular ion mean that the ion makes the cell more negative? No, this isn't determining the charge. So the resting potential isn't the charge of the cell itself. It's not the charge of the membrane. It's the electrical potential energy. It's the available energy to do work. And what we do is we measure from one direction or another. And so because we're using a reference point of inside the cell, the resting potential will be around -70. If we used a reference point just in looking at the a voltmeter, if we use a reference point as the outside of the cell, it would essentially be a positive 70 millivolt resting potential. And so the negative versus the positive is really an arbitrary number. It's more of the electrical energy to do work, available to do the work, and of the reference point of using the inside of the cell as your reference point. So that's taking it a little bit beyond of what you need to know. It's more of, hey, this is the available amount of energy that we have that we can do some sort of electrical type of work. Okay, let's take this a step further. How do each of these guys contribute to our overall resting membrane potential? And the key is the Goldman equation. We can unzip that. I promise this is the most conceptual part of this lecture. This is the hardest slide. So if we can get past this, we're okay. If we have any questions, feel free to ask now. If you're laying in bed tonight trying to get that 8 hours of sleep, and you think of a question, always feel free to email me. But the key to the Goldman equation is permeability. So permeability is what's going to give us our resting membrane potential. What do we mean by that? It's how permeable at rest is this membrane to each of these ions. So now what we're doing is we're essentially taking the Nernst equation and combining it for all of the ions. So now we have the potassium, we have the sodium, and the chloride, and all of their resting potentials being summed up into one equation. And so we have found that the differentiating factor, why some ions play a greater role in determining this membrane potential, where it comes down to is permeability. So what I mean by that is at a resting state, we have those potassium leak channels, right? The membrane is very, very permeable at rest to potassium and not to sodium and not to chloride. So what we see is at rest, the membrane itself is 30 to 40 times more permeable to potassium than it is to sodium. And so where this number changes is it's this value right here. It's this permeability value. So this P is permeability of sodium, this permeability of potassium, this is permeability of the chloride. The strength of this permeability number, the strength of this value is what's going to dictate which resting potential found by the Nernst equation will play the greatest role in determining the membrane voltage. So this equation is the voltage of the overall membrane. What is playing the largest role in determining the potential? It's the permeability. So at rest, we're 30 to 40 times more permeable to potassium than we are to the other two. So the Nernst equation, or the resting potential for the potassium, is the greatest player at rest. So that's why our resting potential for the entire membrane is about -70. So it's going to be closer towards our potassium resting potential. So when we do get the action potential, what happens? Sodium channels open up. And when sodium channels open up, the permeability to sodium skyrockets. And so what's going to happen is the resting potential of sodium will have a larger role now on the overall voltage of the membrane. So the resting potential of sodium is a positive 60. So as we become more permeable to the sodium, the voltage of the membrane is going to start traveling toward that positive 60. So if we go back to this real quick. So as it becomes, this we're at rest, it's very permeable to that potassium, right? Let's see, is this one? We're very permeable to that potassium. So we're going to be at the negative 70. Sodium permeability skyrockets. So now the membrane potential, the membrane voltage is going to shoot toward the resting potential of the sodium. The sodium channels close, and we become even more permeable to the potassium. When we become more permeable to the potassium, we're going to shoot back toward the potassium resting potential. And when that happens, we hyperpolarize a bit, everything closes, we become more permeable to the potassium again, and we have the sodium potassium ATPases, and we reestablish using the concentration that resting potential. So really matters in the Goldman equation, what really matters in anything here is what we're permeable to, what channels are open. The Nernst equation is telling us at rest what their voltages are, what their resting potentials are. And what the Goldman equation is saying, which resting potential is in the driver's seat. So at rest, potassium's in the driver's seat. So we're going to be closer to the potassium resting potential. When we're having the action potential, sodium channels opening up, sodium will now take the driver's seat for a short time. And we'll start heading toward that positive 60. It's called depolarization because we're heading from that negative 70 toward the zero, past it a bit, then we'll repolarize back to the negative 70 region after an action potential. The CL drive hyperpolarization, to an extent, it would help out, but because it does become slightly more permeable as we have all these channels opening up. But as we see, we don't have these chloride channels just opening and closing like we do sodium and potassium, right? So if we don't have those the chloride channels opening up like that, because they don't exist when we're looking at it, at least in the quantity that the sodium and potassium channels do, you'd see like, okay, if permeability is the factor here, and we don't have those specific chloride channels, would it play too large of a role? And for the purpose of the MCAT, it would not. Could a question be about identifying what the membrane is most permeable to at a specific point in an action potential? Yeah, absolutely. You might get a question, at what point in an action potential are we most permeable to? And so, if we're at that can be a little bit more nuanced. If we have a membrane that is at negative 20 millivolts, right? You can't say for sure what it's more permeable to. And the reason why is because if we're at, let's say, negative 20, let's draw, we'd be right here or so, right? You could be on this side where we're more permeable to sodium, or we can be on this side where we're more permeable to potassium. So you need to look at the prior values. If you're given a chart, let's say it's at negative 20 millivolts now, but 10 nanoseconds prior, we were at zero. If we were at zero first and then we head to negative 20 millivolts, you can assume that it would be more permeable to potassium, because that means that the trend is we're going back this way, so we're repolarizing. And so really you need to be able to think about that and take it a step further if you do get asked that question. And then it is something that is fair game. How do you get exact number from the Nernst? That's a good question. You'd need to know the specific concentrations at rest of out versus in, and then you would kind of be able to calculate it, but you don't need to. You don't have a calculator, and that is just pure evil. MCAT is hard, but not that evil. If you don't need to, then P is a constant. So P essentially is a constant at rest, but as things open up and or close, P will change. That is the permeability. So more P, you'll never actually need to know the answer, what the value is. It's more of a conceptual value. Again, I'm not having you actually calculate anything. Just being able to look at these numbers, and if we affect one value, how would that change it? So we have a giant P for potassium and a small p for sodium at rest. So you have a freaking large permeability for potassium, about 30 to 40 times bigger. And so potassium plays the larger role at rest. Yeah, let's see. Will we finish on time? Probably not, unfortunately. I apologize. We went on a lot of tangents earlier. We'll probably go about 15 minutes over. Can we do conceptual example for Goldman? Yeah, so let's say in a made up an arbitrary neuron at rest, the membrane is more permeable to sodium. And it would say, you know, predict the resting membrane potential. So if it's more permeable to sodium, how would the membrane potential change at rest? Yeah, it would be closer to that plus 60, right? Because it's going to be closer to the resting membrane potential of that sodium, because sodium will be in the driver's seat because that's a higher permeability. So let's say conceptually, these channels are permanently open. What happens? This is a little bit difficult. If these channels were permanently open, what would happen? All of them. You'd have no driver in the seat. It would just kind of, everything would efflux, influx, it'd balance out based on concentration. So if you had all these open, you wouldn't have a potential. You wouldn't be able to polarize. You'd be constantly depolarized. And yeah, you're constantly depolarized, but you've never repolarized. And so it's pretty much insta-death. You don't have any control of it or anything. There would be zero membrane potential. It would be completely lost. So yeah, we need some things to be closed. We need some things to be constantly open. So there is control in our body. Let's see. That would be true if the number of these ion channels are the same, right? Yeah. So if they have the same permeabilities, then you can't do diddly squat. It's just going to be open. Everything's going to be where it wants to be. Nothing's going to be where it should be. Eventually, the sodium potassium ATPases would try its darndest to try to reestablish the resting concentrations, but eventually you'll run out of ATP and he'll just give up. So we do need some to be closed. We do need some to be open. And so, yeah, very cool. Alrighty. So that's kind of like the nitty gritty. What would a potential look like during episodes of seizures? So that's more of if you have an excess of glutamate or even an a deficiency in GABA, you can have that can lead to seizures, lead to seizure disorders. What it kind of looks like in seizures is you just have action potentials going every which way, all around the body, all your muscles, right? You're having that rapid contraction and relaxation of all your muscles in the body, right? It's just what you're seeing, action potentials during seizures are just all over the body, everywhere, and rapid signal, and it's causing contraction, relaxation, and thus you do see the seizure. Yeah. So I actually was recently listening to a podcast. Um, People with bipolar disorder sometimes have their limbic system, their emotional part of the brain, is it's a bit wonky, right? And so one of the go-to treatments for bipolar disorder is lithium. Lithium is chemically very similar to our friend sodium. And there was this, I think, the neuroscientist who was kind of just hypothesizing the reason why lithium is a great treatment for bipolar disorder, at least and some people don't tolerate it at all. Some people, it just doesn't feel good. But essentially in the brain, what's happening is in the amygdala and that very emotional part of your brain, the lithium replacing the sodium as that ion that can flow in and out of the brain might not work as well as sodium, and it kind of slows down the brain function of the amygdala, and so it kind of doles it out so that you don't have these manic episodes in bipolar disorder. Yeah. Alrighty. Let's zoom out here. Let's step away from the chemical properties, the electrical potentials, and let's actually apply it. So we do have, right, in the peripheral nervous system and the autonomic nervous system, we have the sympathetic and parasympathetic nervous systems. Let's start with the sympathetic nervous system. So this is your fight or flight. A bear is chasing you. You're running for your life. You're just doing stuff that you're fighting or flighting. So this is pretty much you're very positive, active. I need to run for my life. I need blood flow to my muscles. I need my heart rate to increase. I need my breathing to increase. My pupils dilate. And so this is a part of the nervous system that you cannot control. This is part of the autonomic. So the sympathetic nervous system innervates almost every organ system. And so it can activate the ones it needs to, it can deactivate the ones it doesn't when you're fighting or flighting. And so its neurotransmitter are the catecholamines. So the noradrenaline, the adrenaline, epinephrine, norepinephrine, pretty much synonymous. It gets released by the adrenal medulla. We'll talk about the adrenal medulla and the adrenal gland in the endocrine lecture. But what this is going to do is when the sympathetic nervous system is active, you're just going to prepare your body to deal with these life-threatening environments. So when you need to run, right? When you run, what do you need? You need more oxygen to get to your muscles. You need your muscles. You need blood to go to your muscles. You need your heart to contract harder, contract faster. And so you need to basically prime your body to deal with your environment. And so what's controlling that is your nervous system. Your nervous system is the orchestrator here. It is the captain of the ship. It's saying, okay, we're fighting, we're fleeing. This guy, the sympathetic nervous system, take over and kind of orchestrate what needs to happen. So when you have this going on, all the organs in the body that are needed for the sympathetic nervous system will be activated, others will be deactivated. And so what it uses is it uses adrenergic receptors. So this is something that we'll kind of touch upon in a little bit more next lecture. The peripheral nervous system has different types of receptors, and different types of receptors recognize different types of neurotransmitters. The sympathetic nervous system uses adrenergic receptors, which recognizes catecholamines, the specific adrenaline, noradrenaline. So the parasympathetic nervous system, it can't accidentally activate the sympathetic nervous system. It's quite differentiated. You have different neurotransmitters, different types of receptors, as we'll see soon, but they innervate the parasympathetic and sympathetic nervous systems, they do innervate or actually have nerves that supply the same exact organs. And so we'll kind of revisit the adrenergic receptors kind of in context more next to cardiovascular. There's two different types of adrenergic receptors, alpha adrenergic and then beta adrenergic. So we will come back to that. But if you see adrenergic receptor, your brain should immediately go, hey, sympathetic nervous system. All right. Parasympathetic, so it regulates all the internal organs and glands with rest and digest activities. So these kind of mnemonics, right? Fight or flight, sympathetic. Parasympathetic is rest and digest. So anything when you're kind of just sitting there, right? You're not fleeing for your life, hopefully not. All your rest and digest organs are being activated by the parasympathetic nervous system. Your stomach, your intestines are working with digestion, for defecation. Your kidneys are working in urination, lacrimation. So, the crying, salivating, again, that's a digestive one. Sexual arousal, yeah, you do kind of get that increased heart rate. But when you're super stressed out and fleeing for your life, the sexual arousal doesn't really pop up too much, right? It's sexual arousal is more of when you're at rest. And so that part of your body is controlled by the parasympathetic nervous system. So they do innervate the same organs, but they use different receptors. The parasympathetic nervous system uses cholinergic receptors. And cholinergic means it recognizes acetylcholine. So the peripheral nervous system, or sorry, the parasympathetic nervous system, its neurotransmitter is acetylcholine. And its two type of cholinergic receptors are nicotinic and muscarinic receptors. So if you see nicotinic, muscarinic, think acetylcholine. 100% of the time, it will be acetylcholine that it recognizes. Nicotinic and muscarinic do recognize acetylcholine, but they have different structures. And we'll talk about their structures in the endocrine lecture, and because we talk about receptors there. So yeah, you can also use peptides such as cholecystokinin as a parasympathetic nervous system transmitter. That's more a rest and digest hormone, and we'll talk about that one in the adrenal, GI, and kidney lecture. So the autonomic nervous system, they're antagonistic and complementary, right? So they innervate the same organs, but they do opposite functions. And so they are constantly battling and working together to control the function of all your internal organs, of all your organs. So when you need to relax, the parasympathetic system will take over and the sympathetic system will kind of shut down for a bit. But let's say you're sitting, all of a sudden there's a loud bang and you need to flee for your life. Sympathetic system will try to overrun parasympathetic. And so they're antagonistic, meaning they work against each other, and they're complementary. They do the same exact organs, and they're one being off, one being on, will help control your bodily functions. And so if we go back to this slide, right, this is the spinal cord. In red, all the red nerves here, those are our sympathetic nerves. The blue ones are all our parasympathetic. And so you see it's highly organized, it's separated. So you're never going to have a lot of, issues with them being confused over each other. You're not going to have accidental, what's going to call just one functioning when others not. When you see where they are, the parasympathetic nervous system is located in the medulla, as you can see right here. So that's a big guy for controlling when you're at rest, your heart rate, your breathing rate. So there's a lot of cranial nerves. So cranial nerves 3, 7, and 9 are all parasympathetic nervous system. You don't need to know the cranial nerves, but then you also have parasympathetic down near the sacrum. So areas of the spine S2 through S4, so in the sacral spine, you do have some parasympathetic. And then the sympathetic nerves are all in the thoracic spine and lumbar spine. So what happens is, depending on injuries to the spine, entries to the spine here can really, depending on the location, that'll tell you what's going to be impaired, what's not going to be impaired. So, for example, I had a patient 2 days ago now where she was screwing around and had hurt her neck. And so this is where the cervical spine is. This is where your neck is. She had deformity in here. She's still breathing, right? Heart rate is still going because we didn't affect the medulla at all. But she had a really hard time with movement. She couldn't move anything. She defecated herself, urinated herself, because she just lost control of that. And the injury, where it is, can tell you what's going to be affected. And so yeah, everything is highly organized in the spinal cord. Let's see. So cranial nerves are nerves that go from the spinal to the organs. And so no, so cranial nerves there are specific nerves, there's 12 of them, and that go straight to the brain. So there's the, oh God, I forgot them all. There's the vagus nerve, hypoglossal nerve, all these guys that have their very specific functions. They go from organ straight to the brain. So those are the cranial nerves, right? So we do have the medulla as part of the brain, and that goes straight from brain to organ. So the everything here is not cranial nerves. These are spinal cords. These are come from the thoracic vertebra. So T1 to L3 are all your sympathetic nervous system nerves. So yeah, so don't get that mixed up. Let's see. I think cranial nerves participate in both SNS and PNS. They mostly participate in parasympathetic. Yeah, we do have the medulla that's controlling your heart rate. But what that is we have our heart right here, right? We do have cranial nerves that are innervating it, but we also do have sympathetic nerves. So that's what's causing it to speed up. Let's see. Restate which spinal regions are. So, okay. So when you do have the brainstem, so this is the brainstem is parasympathetic. And then the sacral region is also parasympathetic. So specifically S2 through S4. What I mean by S, we have 5 sacral vertebra. So we have S1, which is sacral 1, vertebra 1, sacral 2, 3, 4, 5. This is the coccygeal region, which is just a bunch of fused vertebra. And then, which this you don't need to know. I'm just trying to show you that it's highly organized and you don't have a lot of overlap in that. Hurting one region can do a lot of different things. It's more of hurting one region and severing the spinal cord here. You're just going to affect everything downstream, like down this way, because it can't go back to the brain. But the sympathetic nervous system goes from T1 to L3. So we have 12 thoracic vertebra, and then 5 lumbar. So L1 is lumbar region. You don't need to know the regions of the spine, but you might get it thrown at you in a passage, just a jargon, just to confuse the heck out of you. If you're familiar just with the terms, then that's, sufficient enough. Okay. If we want to look at what the parasympathetic and sympathetic nervous system does to each organ, so digestive system, parasympathetic increases peristalsis. What's peristalsis? We'll talk about that in like 3 weeks. Sympathetic, if that's active, you're going to decrease activity of the digestive system because if you're running for your life, why expend energy digesting food? You don't need that. So kind of just look at it and see like, okay, if we're running for our life and we're in the lungs, the parasympathetic system, what it's going to do, if we're just resting, it's going to constrict the bronchioles. We don't need lots of air coming in and out. We're just resting. But when we're running for our life, we need to increase air exchange. And so we're going to dilate the bronchioles, the distal airways, which we'll talk about next week, and try to get more air in and out. So this is something you can look at and be like, oh, okay, so this is what it does to each organ. Alrighty. So in the spinal cord, we do start to get some level of processing. Oh, you love this mnemonic. Yeah, same Dave. I freaking love same Dave. It is quite useful. It when you're stressed for the MCAT, I swear, I promise, when you're taking that exam, some of the most simple things are they just when you're stressed can escape your mind. And I love mnemonics and just very simple ones, just like same Dave. I can remember that. And so when you're stressed, just kind of use that as a crutch sometimes, just to avoid silly mistakes. Um, so we do have some sort of processing, very primitive, primal processing levels that does exist in the spinal cord, and that where that happens is during reflexes. So when you're a kid and the doctor's hitting your knee with that hammer thing, and your leg just kicks out, right? So that's a reflex. You're not controlling that. You can't stop that. And the reason why is because what's happening is you're hitting the patellar tendon, which is causing a little bit of stretching. The patellar tendon is going to pull on the quadriceps. When you pull on the quadriceps, the sensory nerve is going to send it to the spinal cord. The spinal cord is just going to be like, oh, we need to do a motor response. So it's going to cause the quadricep to contract. And when the quadricep contracts, you kick out. So you can't control that. The spinal cord is doing that processing for you. So it's doing that processing, but it's also at the same time sending information to your brain. And so you can actually, you'll have that response, you'll have that motor response, that effector um, type response happen before you even really process it in the brain. That's when you touch something hot. You touch something hot, it's going to your spinal cord, your hand pulls away. And if you ever kind of notice, it's almost you pull your hand away before you kind of realize it's hot. You pull your hand away, and it's like, oh, wait, that was, ow, I just, seared myself. Happens quite frequently to myself. So I have a lot of personal experience. I try to base a lot of things. I want to talk about that through my personal experiences. So when you think about to yourself, just try to think of wow, what different reflexes do you have? Right. I mean, everybody, I think it's pretty ubiquitous to have the patellar tendon one done. I may just burn myself more frequently than the common folk, but that's fine. It happens. So what is same Dave? What is this mnemonic? So this same Dave applies to reflex arcs. So when you do have that reflex arc, let's say we hit that patellar tendon, we stretch the quadricep. The sensory nerve is going to be like, ha, I sense it stretching. And so the sensory nerve is going to take it to the spinal cord. The sensory nerve is afferent. It's being accepted. I'm going to type that out because I swallowed some letters. Let me send that in the chat. Let's see. Accepted. Ah, cool. The afferent nerve is accepted into the spinal cord. And then it's going to do some processing. And when it goes to the processing and the spinal cord, it's going to send something out through a motor nerve. So sensory is being accepted. Sensory is afferent. The motor nerve, the motor neuron, is going to be efferent. It's going to exit. Exit. So this is this works everywhere. Afferent is being accepted to wherever it's going. Efferent is exiting. Very cool. So the sensory afferent, motor efferent. But then you might also get asked, what side of the spinal cord is it entering? So same sensory afferent, motor efferent. Dave, dorsal afferent, ventral efferent. So what is dorsal? If you ever think of fish, I absolutely love fish. I'm obsessed with aquatic life. The dorsal fin is on the back, right? So the dorsal is the back side. So if we actually look at this, and this is a patient, this is the posterior or the back side of the patient, and the ventral root is anterior. So front, anterior, ventral, all synonymous. You'll see all of them written everywhere. So kind of be familiar with what each of them are. So dorsal afferent, ventral efferent. Nerves that enter into the spinal cord enter through the dorsal root. So this is the dorsal root. Nerves that leave the spinal cord exit through the ventral root. This is the ventral root. So it's kind of come in. Sensory is afferent going through the dorsal. So sensory by what's that? What is it? Freaking elementary school commutative property. Sensory is also dorsal because they're both afferent. And all the motor guys, they leave through the ventral root. They're efferent. All the motor are ventral. I think that's the commutative property. The way you remembered ventral versus dorsal is that when we vent through our mouth. That is brilliant. I had never heard that one either. Wow, I'm learning a lot of different little tricks from you guys. I like it. I appreciate it. I remember it via dorsal and then dorsal fin. So yeah, so same day of reflex arcs. Sensory afferent, dorsal efferent, or sorry, dorsal afferent, sensory afferent, motor efferent, ventral efferent. So that's how I remember it. Same Dave. Sensory, so sensory is dorsal, yes, because sensory are afferent nerves, and all afferent nerves are dorsal. So sensory is thus dorsal. Yeah. So all reflex arcs are the same, essentially. They all function with same Dave. If you see reflex arcs in a passage, write on your paper, on your scratch paper, same Dave, just to keep it straight in your head. Yeah, I will re-explain that. So by the commutative property of mathematics, if A equals B and B equals C, then A must equal C, right? And so if sensory is afferent, and all these afferent guys enter through the dorsal root, then that means the sensory nerves must enter through the dorsal root. And if all these motor nerves are efferent, and all the efferent are ventral, exit through the ventral root, then all motor guys must leave through the ventral root. And so what the way I memorized it, I read it on my scratch paper, same Dave. So all sensory nerves are afferent, they go toward the spinal cord. That's right, because what use would it be if a sensory nerve went to a muscle? It's like the muscle is not going to process any senses. What's going to happen is the senses that the muscle experiences will go to the spinal cord and thus the brain, so you can feel it. If sensory information was sent to a muscle, the muscle is going to be like, what the heck do I do with this? I only really deal with, do I contract or do I not contract? And that's a motor nerve. Motor nerves control if you're contracting or not. So same Dave. Sensory are all afferent, all motor are efferent, motor to the brain. So also, what good would it be to send a motor signal to the brain? The brain can't move. It's not going to want any signal to that. And so the synapse between these two guys exists right here inside the spinal cord. That's where you're going to get some processing. So there will be another nerve that sends it to the brain. There may be a neuron in between the two called an interneuron. It really just depends on what specific reflex arc we're looking at. But all reflex arcs will deal with the same Dave. All the sensory guys are afferent, all the motors are efferent. And then the dorsal root takes in afferent nerves, the ventral root sends out efferent nerves. So that makes sense. Alrighty. Almost done. I'm keeping you guys over. I apologize. Okay, so when we do take information in, it goes to the brain, because how do we kind of integrate that? How do we take in sensory information and cause a downstream effector response? So everything our body does is take in sensory information, sensory integration, and cause a downstream response. So let's say our set point for our body is 37 degrees Celsius. That is, you'll never get it in Fahrenheit for the body temperature for humans. The cat pretty much just deals with Celsius here. So 37 degrees Celsius is at homeostasis, our target temperature. Let's say our environment, we're feeling mighty cold. We have a low temperature. If we have a low temperature, we have to take in that sensory information. So we're going to, the blood might be a little bit cold, and the hypothalamic receptors, as we're getting some cold blood, it's going to sense like, oh, wow, this is a couple degrees or a degree less than what I would like it to be, it'll realize that. You have cutaneous thermoreceptors, the ones at your skin level. So you have thermoreceptors that are sensory receptors that will send information to the integration center. The integration center will be the thalamus and hypothalamus, and you'll cause downstream effect. So you can do different ways. You can do sympathetic neurons that sympathetic you can't control. You can't tell your blood vessels to constrict. They just do it on their own. So the integration system, your brain, will tell via the sympathetic neurons to constrict your blood vessels. And what it's going to do, that's going to pull the blood away from your skin. It's going to pull it away from your environment, from the cold environment, and try to keep a more core body temperature to heat it up. And you can also, somatic motor neurons, to your skeletal muscles, telling you to contract, relax, very, very rapidly. And cause shivering. What does shivering do? It is causing a byproduct of heat. And so you can not only constrict your blood vessels, pull it away from the environment, but also cause shivering to generate your own heat. And what that's going to do is that's going to cause an opposite reaction, a downregulation on our sense of that low temperature. So it's going to try to do the opposite to that low temperature, meaning raise the temperature. And so your hypothalamic receptors and your cutaneous thermoreceptors are both going to realize that, hey, we got our body temperature back up. We can stop now. And so what's going to happen is all this information goes to your brain, goes to the integration center. The integration center can cause downstream effects via your nervous system, tell things to constrict, tell muscles to contract, or do the opposite. As you can see, we can also do very similar things with the brain and the hormonal system. And that's where the nervous system and the endocrine integration will overlap. They will work together to do a lot of different things. And that's something we'll talk about later, specifically the HPO axis. So the HPO axis is something that we'll talk about in much, much greater depth in the endocrine lecture. The hypothalamus will take information from the nervous system, send it to the pituitary. So HPO is hypothalamus, H, P, pituitary, and then O, target organ, and we'll send hormones to different target organs. So the integration center's question is the thalamus. For the most part, yeah, there's some things that will be more processed in the hypothalamus as well to do a hormonal response, but the thalamus and the hypothalamus work together as the integration center. Your brain is an overall, basically a computer. So if you guys are okay and want to go over passages on your own time, you guys are free to go. I will see you next week. For those of you who want to go through some passages, we'll go through that right now as a group. I'll have you guys read a passage and we'll go through each of the questions. I have 2 passages here. If you do have somewhere to be, sorry for keeping you over time, 5 minutes over, but I'll see you next week. And I did enjoy today. So we'll start in a couple minutes for those who do want to stay. In the PDF, the solutions are there. They are already highlighted, but if you do want to discuss why, the answers are what they are. Feel free to email me. Yeah. I appreciate you too. And this is one of my most boring lectures, so I promise you, I hope you guys enjoy it. It really just geek out every single time. All right, for those of you who want to stay, I'll give you a couple minutes to read this. This is kind of just taking information from the passage, being able to kind of sift through it and answer some questions. So we'll give you a few minutes to read this. When you do have an answer for this first question, do send it in the chat so that I know you guys are done and see how you guys are doing. So yeah, go for it. Alrighty. If you didn't finish, no worries. Let's go through this together. You guys, awesome. So, of the answers I've got in the chat, it's looking good. So let's actually go through this. Um, I'm sure you guys have done passages so far in these 3 weeks, and as you know, it's just like, hey, we learn all these topics, the other stuff. Then they just throw a passage at you that is jargon up the wazoo. Jargon is terrible. It's just there to confuse you. It's really just there to get you to realize, hey, I don't know this, and kind of freak out. And so it's kind of just staying calm and working with what we know. So you may have heard organophosphate before. Probably, maybe some of you have seen sarin gas. Maybe some of you haven't. You don't need to know what sarin gas is. It kind of just tells you it's a gaseous organophosphate that is commonly used in chemical warfare. It's a nerve agent that happens via inhalation. And so how it works is an irreversible inhibitor to acetylcholinesterase, an enzyme that catalyzes the breakdown of acetylcholine. So if we kind of think about that, and I said in the lecture, acetylcholine is one of those neurotransmitters. If we have one of those neurotransmitters and we are blocking one of the enzymes to break it down, and then you're going to probably have a lot of postsynaptic signaling, right? You're not going to be able to break it down. You've inhibited one of them. So it works the same way with serotonin and MAOIs. It is essentially preventing the enzymatic breakdown of this neurotransmitter. So you're going to have postsynaptic signaling, a lot of it. There's a question, what do I think are good resources for studying physiology? A little tangent. I suppose I practice questions, definitely. Obviously, if you need to review information, use this, and I'm huge on practice questions a lot. So a lot of QPACs, UWorld, full-length exams, and whatnot. I just recommend a lot of practice questions, as many as possible, so you can practice learning the patterns, where to pick out the information, where to ignore jargon, and taking this basic information and learning to piece it together to move forward. So yeah, I definitely, physiology is more one of those application type things rather than memorization. So this question asks, given the sarin causes irreversible damage to a cell's acetylcholinesterase enzymes, which medication would be most appropriate for an individual who has already been exposed? So they've already been exposed. They do for sarin gas for nerve agents. They use both of these medications, atropine and pralidoxine. So you don't need to know anything about any medications. And so that's in there just to stress you out. That's there to be like, oh boy, I don't know these medications. Increase those cortisol levels. We'll learn about cortisol in the endocrine lecture, and kind of cloud your judgment a bit. So for the most part, when I do this type of question, I don't look at the medications. I'm going to ignore that first word. Where I'm looking is the second part of each of these answers. So this is someone who's already been exposed to this gas. It causes, excess signaling because you are not breaking down this neurotransmitter. The acetylcholinesterase, it is an enzyme that breaks down the neurotransmitter. That neurotransmitter is going to continue binding to that postsynaptic neuron and signal. You're getting a lot of downstream signal. They've already been exposed. And it's irreversible. So that's a good thing to know. You cannot reverse it. If it happens, it happens. So which of these would be the best solution? A, let's look at it. Since it would remove sarin molecule from the enzyme, irreversible. Nope, that's not going to do anything. The damage is already done. Since it would remove the affected cells. If you found a medication that removed affected cells, you'd win a Nobel Prize. You would cure cancer. You would cure a lot of things. So that does sound like a good option because it sounds absolutely fantastic. But we cannot remove affected cells with such precision. Plus, it is a very systemic Systemic problem. So that is also going to be another issue. That's more of like a common sense type kind of thinking one. A lot of people either choose between B or C. So if you were thinking B, no worries. It's usually for this question, I get a 50-50 split between B or C. C, atropine, since it would counteract the effects of the irremediable acetylcholine surge. So this is something where having that surge, it's inevitable. We're causing irreversible damage. It will be signaling. So what this is going to do is this is going to target the downstream effects. So whatever the acetylcholine surge is doing downstream, atropine is going to try to counteract that. And then D, since it would reactivate inactive enzymes, no, it is irreversible. And it says that in the question. So the answer for this one will be C, right? Because the surgery is going to happen no matter what. We're going to now look at what is downstream. So very well done for you guys who got it. He did not need to know a damn thing about sarin, atropine, or pralidoxine. So can you think of it like this? Let's see. Is D false because reactivating it won't work since sarin is still there? Not only is sarin still there for the time being, but it causes irreversible damage. So the key for that one is irreversible damage. So that is partly why D is false, but there will be sarin that is still there. Yeah. Those enzymes no longer work. They're out of commission. Next one. This is kind of looking pathways. Let's look at it and see if you can picture this in our head. Enzyme X is activated by the presence of acetate ion. How would you expect the presence of sarin to affect the rate of enzyme X? So let's take information from the passage and put it into a pathway. All right, so I'm having a little bit more trouble with this one. Let me get this chat box out of the way real quick. It's in my way. Oh, gosh darn it. So this is this is taking in OChem information. So you are right. So for OChem, it does overlap. And so what's happening here is it's saying enzyme X, which we don't know what enzyme X is activated by the presence of acetate. Acetate increases enzyme X activity. How would you expect the presence of sarin to affect the rate of enzyme X? So this is where you kind of like you need the OChem information. It says right here, acetylcholine is an ester of acetic acid. Sarin inhibits an acetylcholine esterase, so it cleaves esters. So if we cleave acetylcholine, which is an ester of acetic acid, if we cleave that acetylcholine, one of your byproducts will be the acetate ion. So you need to kind of take the OChem information and being able to kind of piece together, if we have this acetylcholine esterase, it breaks down acetylcholine into the byproduct of acetate ion. But if that serine is inhibiting this acetylcholine esterase, you're not breaking down the acetylcholine, you will not create the acetate ion. So if you're not creating the acetate ion, it's not there to increase the rate of enzyme X. So you would thus decrease the rate of enzyme X in the presence of serine because you won't have that acetate being produced. For those of you who are struggling or thought, hey, does that make sense? And if not, any specific questions on where we might have gotten lost? This is something where you do have to take a bit of OChem knowledge and apply it into a bio scenario.
I have a quick question.
Yeah, what's
So,
up?
I guess the takeaway here was that the acetylcholinesterase creates the acetate ion, and then we would figure out the rest from that.
Yes, that is the key to actually solving this. Knowing that the serine blocks that acetylcholinesterase will decrease that acetate ion that's not being produced. So that is what you needed to extract from it, and then extracting that piece of information would help you downstream. There's another question. You chose B without thinking of OChem only to see that it was inhibitor. Can you reword that question? I don't exactly get what you're asking there. Just to see that it was an inhibitor. I mean, I guess actually, I think I know what you're asking. I guess that you saw that it was an inhibitor that you would have. That would have been a valid reason, but you can't necessarily make that jump just because it's an inhibitor. You just have to know that if the acetate is increasing enzyme X and the inhibitor is decreasing the amount of acetate ion, you can make that jump. So just make sure, just because you see inhibitor doesn't mean it's going to decrease the rates of everything. So a great example of that is the next question. Where did my annotate tool go? There it goes, clear all drawings. I have another pathway for you. Enzyme Y is deactivated by a downstream effector molecule that are synthesized following acetylcholine receptor activation. How would you expect the presence of serine to affect the rate of enzyme Y? All right, we have a nice split here. Okay, so let's go through this. So enzyme Y is deactivated by a downstream effector molecule that is synthesized following receptor activation. So receptor activation is going to decrease enzyme Y. How would you expect the presence of serine to affect enzyme Y? So what serine is going to do is it's going to be an irreversible inhibitor to acetylcholinesterase. So if we are blocking the enzyme that breaks down the acetylcholine, we're not breaking down the acetylcholine. So the acetylcholine is still going to be there. So you're going to have leading to excessive activation. So if you're having acetylcholine that's still there, you're going to have more downstream effectors that are synthesized following the receptor activation. So if you have more signaling, you'll have more of these downstream effector molecules from the receptor activation. And these guys, these downstream effector molecules, deactivate enzyme Y. You'll also decrease the rate of enzyme Y. So there's a question, if the downstream effector molecules are synthesized with acetylcholine receptor activation and serin excessively activates acetylcholine receptors, then enzyme Y will be deactivated more. Exactly. Sophie, you got that right on the button. Yeah, you got it right on the button. Awesome. Express your thought process to show a flow chart of how the reaction occurs. Yeah, so in my mind, I draw a lot of pictures in my mind. That's how I work. So let's see. In my mind, I see enzyme Y. Enzyme Y. So the acetylcholine in my head, so ACH has a negative effect on enzyme Y. So enzyme Y is deactivated by downstream effector molecules are synthesized following receptor activation. So more acetylcholine will have a negative effect on enzyme Y. So if we have something up here that is the serin, serin is causing a increase in acetylcholine signaling. So serin has a positive effect on the increase of acetylcholine. Acetylcholine deactivates the rate of enzyme Y. More serin equals more acetylcholine signaling, meaning further decreased rate of enzyme Y. So enzyme Y deactivated by the downstream effector molecule. So more acetylcholine has a negative effect on enzyme Y. And serin blocks acetylcholine degradation. If we're blocking acetylcholine degradation, we'll have more of it. More serin means more acetylcholine, which means lower activity of enzyme Y. That makes sense. So pathways are huge. It's the information's all here. It's can you extract and keep things straight? So you do have that scratch paper next to you. You'll have that. So I definitely recommend, at least until you deal with enough in pathways that you get really, really good at this, draw it or write it down. Keep it helpful. So for my MCAT, for some reason, most of my passages were all pathways and all hormonal pathways. And so, we'll get through the hormonal pathways, later on. I think in November we get to that. But it's more of a, was I able to sit there? I drew it out. They gave me more information. I added the information to the HPO axis, which I already knew, and I kind of to keep everything straight there. This is an agonist, meaning it has a positive effect, or this is an antagonist, meaning it has a negative effect. We'll get into more in the pathways later on, but keeping it straight is definitely, half the battle here. All righty. So let's keep on cracking along. Think we have a couple more in this passage, I think. So, no, this is a new passage. Very cool. I'll give you a couple minutes to read this passage. And when you get the first one, first question, type it in the chat. Alrighty. So looking good, looking good. So what type of ion channel would mainly be opened by electrical stimulation during action potential? For this question, you actually don't need to read the passage at all. So what ion channel is opened by electrical stimulation? Electrical stimulation opens voltage gated channels. There are questions, ligand gated channels. Those do occur on the postsynaptic neuron, right? Binding to that neurotransmitter. The neurotransmitter is that ligand. Potassium leak channels, those are always open. They're not opened by electrical stimulation. Sodium potassium pumps, if they have their substrate and they have their ATPases, they'll be functioning. So a lot of people choose, usually for this question, people are usually deciding between A and D just because they see sodium and potassium. There's like, yes, those are the ions that flow through. So that is true, but it's voltage gated ion channels that let in the potassium and that sodium. Yeah, so Michaela, yeah, exactly. So what's specifically opened by the electrical stimulation, those are the voltage gated channels. And so the voltage gated, meaning that the voltage, the change in voltage caused by an electrical stimulation is what opens them. So that is what this question is asking. Ready. Next question. I need to get rid of my annotation tool. The voltage gate channels. Next one. If mice with this disease do lose myelin with use, what change would a scientist see in the conduction speed of action potentials along the axons of the older mice when compared to the younger mice? Alrighty, well, looking good. So we're looking at a demyelinating disease. So mice gradually lose myelin um, with use, right? And so this is saying the question asking if the mice with the disease lose it with use, what change would you see in the speed of action potentials along axons if we have older mice compared to younger mice? So if we're losing it with use, obviously the older mice are going to use their myelin more, so they're going to lose more myelin. So this is what the question is asking. What difference do we see in the speed of action potentials with mice with less myelin compared to more myelin? And right, and myelin is that insulator, it speeds up the action potentials. So if we have less myelin, we'll have a decrease in the action potential speed because these older ones used it more. So very well done. And the electrical response is being recorded on what type of nerve? This one usually trips people up. So let's see if we can get this one. All right, got a few answers. So this is like, okay, we have to find some information here because we're monitoring the electrical response. It's like, does we have to find what type of nerve, we need to search the passage for this. And so if we look through and kind of read this, see where are we being recorded? So it's saying, oh, okay, record the electrical response further away on the nerve, closer to where the axons enter the central nervous system. So further away is where it's entering the nervous system. So if we have our spinal cord right here, and I'm going to be Picasso right now, I'm going to draw this. Honestly, I feel like this is pretty good. So we have our ventral root, we have our dorsal root, we have our reflex arc. We're just kind of looking at it like that, right? If we're looking further away on an axon, where it enters, and if we're entering it, what type of nerve is that? That's afferent, right? We're being accepted. Let's see. You're great. So that was my next point. Fantastic. You can kill B and D right away. They are the same thing, right? Motor or efferent, same Dave. You can't be one or the other. They are the same 10 times out of 10. So that is something that is a great point. That was my next. I was going to bring that up. Not going to be it. Interneuron. Interneurons are, as I said briefly, they're in here. They're in the spinal cord already, and so we are measuring on the nerve where it enters in the CNS, in the central nervous system. In that spinal cord, we're not quite there yet, and so we can cross off interneuron as well. Kill B and D right away. They're the same thing. You cannot answer B without it being D, so it has to be A. That is the last question for today. For those of you who did stay 40 minutes over, I sincerely apologize. Yeah, so that is the end for today. I appreciated you guys coming here today. Hopefully, you guys enjoyed it. I'll see you for the next like 6 Saturdays in a row. And have a great rest of your day. Have a great rest of your weekend. I will be here for a couple more minutes. I need to get ready for work, unfortunately. But if you have any questions, open door policy, virtual open door policy, send me an email. We can set time up to meet, or I can answer any questions.